Okay. So we know that when you have a solenoid and an iron core in it, and if it has a constant electric current, then it doesn't fight anything, right? It's happy. But as soon as you turn off the current, or if you start the current from rest, that's when we get that induced voltage, because we get that induced magnetic field. Because nature wants to keep the magnetic field the same, so if you start changing that magnetic field by changing the current, then you get an induced magnetic field that tries to oppose that change, right? And that induced magnetic field can start a current in another wire. It can induce a current. And so when we have a solenoid, the symbol for when we put it in the circuit looks like that. It doesn't look like a real spiral-looking thing. It looks more like this. So this is a solenoid, and if you take the solenoid and you put an iron core in it, or a magnetized core in it, you get what is called an inductor. The four most basic circuit elements involved, including batteries, excluding things like wires and light bulbs. You got batteries, you got resistors, you got capacitors, you got inductors. And then you learn, after you go beyond this class, you learn about diodes and transistors and all those kinds of things. But an inductor is simply a solenoid with an iron core in it, or a magnetized core in it. Your key fob. If you ever next time you have to change the battery in your car key fob, there's probably some inductors in there. I know there is in mine. There's 2 inductors in my key fob. And what's that?
I don't see it.
It's on the inside, Connor. So it's called an inductor. Why is it called an inductor? Because it has a property called inductance. Okay. And that's essentially how we quantify the fight. Right? How we quantify how much that inductor is going to fight a changing current. Okay? So we're quantifying a quantification of the fight, put fight in quotes, because it's not consciously fighting something. The fight against a changing current.
So be resisting a changing current as well?
What?
Could you use the word resisting there?
Yeah.
Resisting against?
Yeah. Just know that we're not talking about resistance. You end up with over an instantaneous time interval. You end up with a phenomenon similar to what would happen in a resistor, but it's going to change, right? The resistor resists it by the same amount no matter what. That we measure that resistance in ohms. The fight itself against I'm jumping ahead. You're jumping ahead. Stop it, Bradley. Okay. Now it turns out that when you have an inductor and you have a changing current, and so I'll call that di dt. If I have a di dt, then there's going to be a changing magnetic flux, right? And so magnetic flux, actually, what's the best way of explaining this? Oh, sorry, I'm jumping ahead.
I'm jumping ahead, Bradley.
So because inductance starts with the letter L, the symbol is a capital L. Okay? The symbol for inductance. And again, it is how we quantify. It is a numerical value. And it is proportional. The inductance is proportional to the magnetic flux. And that should make sense. Right? I did this backwards. This is true, but hold on. Right. Let me just give you the definition. Another definition for magnetic flux, it's L times the current. And we'll elaborate on this in a second. L is the inductance. I equals current. Normally I go into a much longer derivation of this, but I'm not going to because it's quite a few pages in here of stuff that we just don't have time to deal with. But this just gives you another equation for magnetic flux. That's not on the formula sheet. However, there is something on the formula sheet that gives you the same information. Okay. So whenever I have a current, and even if it's a steady current, because if you have a steady current, you have a magnetic flux. You just need a changing magnetic flux in order to induce a voltage. So if I have a steady current, I get a magnetic field going through the solenoid, through the inductor. And that magnetic flux, right, the total magnetic flux through the entire thing is the inductance times the current that goes through it. Okay. What's that? Yeah.
No. They're within the first 10.
That's fine. Whatever.
Did you use your E-hole pass?
Now, since the induced voltage, because I get an induced voltage if I have a changing magnetic flux, since this is true, and this is also true, then my induced voltage within an inductor is going to be negative d dt of L times I. And as we'll see, just like the capacitance of a capacitor is a value that doesn't change whether the capacitor is charged or not, the value, the inductance of an inductor doesn't change, regardless of whether there's current going through the inductor or not. And so L is a constant, so it's going to be negative L di dt. This is on the formula sheet. The voltage induced within an inductor is the negative of the inductance times the rate of change of the current through it.
So there's no rate of change, or there's no changing current,
There's no induced voltage, and it just acts like a wire, actually. Right? So it's just going to be a bare wire. That's not, because you need that changing magnetic flux in order to induce a voltage that's going to fight the current. Which, I mean, he's out of the restroom now, but which is kind of like, they act like kind of like a resistor at that time. So we'll talk about that.
I thought you were going to say they kind of act like Bradley.
They kind of act like Bradley, yeah. Okay. Now, real quick, I'm going to go through this rather quickly, so just bear with me, please. Let's say I have a solenoid, because I do want to prove this to you, a statement that I made a minute ago. So I got current going up this way, and they got current coming down this way. Let's say again?
It must be from non-conducting ink from the marker. That's not solenoid.
Yeah, you can't prove it. I don't believe you.
Out in the pod with you. Okay. Now, remember, we know that the magnetic field here, let's just assume that it's got the configuration where it makes a magnetic field that way within the center of the solenoid. This is on the formula sheet. The magnetic field for a solenoid is mu naught times N times I, where N is the number of loops, capital N divided by the length of the solenoid. So N, lowercase n, is the density, the number density of the loops. That is explained on the formula sheet, so that's not something you have to remember. But this is the Bunny equation. Okay. And then if I know the magnetic field, I can calculate the total magnetic flux. This is similar to things we've already done. The total magnetic flux through this is going to be the integral of B dot dA. And so that's going to be the magnetic field. Mu naught is a constant, N's a constant. In this case, I is a constant. And so it's going to be mu naught Ni times the integral of dA. Now you got to be careful here because dA is the area of the circular loop, right? But you got a bunch of those areas. You got one of those areas for every circular loop. And so you got to multiply, when you do this integral, it's going to be mu naught Ni times pi r squared, where this is r squared. That's just r, not r squared. But then times capital N. right? The total number of loops that the solenoid actually has. Well, I got little n and I got big N. I just want the I want an equation that gives me the magnetic flux, which I will then use to talk about the inductance, magnetic flux inductance. So I want to write N as capital N over L. And remember, that is on the formula sheet. So phi B is going to be equal to mu naught. I'm going to say mu naught. I'll just do it. N over L times I N pi r squared, which we can obviously simplify. It's going to be mu naught. How do I write it here? N squared pi r squared. There's a point to this, I promise. There's a point that I'm trying to get to. Over L.
Teachers and students, pardon this interruption. The fire alarms are being worked on. If the fire alarms go off, please disregard. We'll let you know if something happens that we need to evacuate. But disregard any fire alarm for now. Thank you.
What happened to I?
It's in there, you just can't see it.
It's in there, you just can't see it.
Then
It's
it
right-
could be ruined.
right there.
R-U-I-N. I ruin over L.
Yes, I'm sorry. But I have a definition for magnetic flux in terms of inductance now. And again, there is a reason that this is true. It has to do with proportions, but I'm not going to get into that because I'm trying to get this through this as quickly as possible. Phi B is Li. So I have two expressions now that I can have for this. So I was jumping the gun here because the i's actually cancel. Which gives me an equation for inductance. The inductance of a solenoid is going to be mu naught N squared pi r squared over L. Like capacitors, whose capacitance is due solely to the geometry, the construction of the capacitor, inductors are the same thing. The inductance of an inductor is due solely to the geometry of the inductor itself. It's due to the total number of loops in the inductor, the radius of those loops, and the length of the inductor. Everything else constant. And so that tells you whether, and you might want to think of it this way, whether an inductor is, quotes, charged or not, but it doesn't get charged like a capacitor, but as you'll see, it's kind of similar. Whether it's charged or not, whether it's storing energy, I should say, within the magnetic field, the inductance is the same. Just like a capacitor, whether it's charged or not, has the same capacitance, it doesn't change. Inductors are going to be the same way. Okay? Yes, but we neglect usually you have the inductor in the same circuit with either a capacitor or a resistor, and so the resistance of the wire is going to be negligible.
If you think about
Not really, but for us, yes. Good question.
if you think about it, that's still technically a function of geometry, but like on a 9%,
Yeah.
very nanoscopic scale of the elements. In the
Yeah, but
about it.
you're making my brain hurt. Stop it.
He took too long. I think he was complicating in the bathroom.
Okay. So things you want to remember. This is on the formula sheet. This is not. So some of you might want to just magnetic flux is Li. Yes. All right. Now I'm going to go back to a circuit that we've dealt with like early on when we first started studying circuits, before capacitors, before we invented magnetism. And we were just studying, say, a circuit that looked like this. Let's actually put a capacitor in here. I lied.
Oh, we're getting spicy.
Got a switch, got a resistor, got a capacitor, got a battery voltage V. And I started kind of going over it like this before, but it didn't really work out that well. It really didn't matter so much, but when we start throwing inductors in circuits, things get a little wonky, so just bear with me. My battery, I know, has positive charge on this side, negative charge on that side. More potential energy per unit of positive charge here than here. And then as that energy goes through the resistor after I close the switch, it loses electric potential because it loses electric potential energy in the form of heat for a resistor. And then it starts loading positive charge on this side of the capacitor and negative charge on that side of the capacitor. Okay. Now, if I was to draw an electric field within each circuit here, and we are assuming that the resistance of the wire is 0. If I was to draw the electric field within the battery, it actually points in the opposite direction because electric fields point from positive to negative. The electric field within the resistor points this way, right, from positive to negative. The capacitor, the electric field points from positive to negative, right? So the thing is, we've defined this new thing. Well, we already know that the potential difference across any of these, and really this is the general equation, the potential difference between 2 points in space where there is a potential difference is the negative integral of E dot dr, right? But then we learned that when we have an induced voltage within an entire loop of wire that doesn't technically have a starting and ending point, we can say that the integral, the closed loop integral of E dot dl is going to equal 0 if I have a closed loop, because Kirchhoff's voltage law says that the voltage of the sum of voltages around any closed loop is going to be 0 every single time. Okay, so I'm actually going to write this kind of like this. Let's say I want to know the potential difference as I go around this entire loop. But let's use this form of the equation, and let's leave that off for now. You guys see the similarity between these two, though, right? And these are pretty much the same thing. It's just dr is usually just through space, arbitrary space. dl is usually when you're going around some kind of loop, right? Whether it's a wire loop or an Amperian loop. Well, if I was going to use this to calculate the total voltage as I go across around this entire loop, the potential difference, let's say I start at the positive terminal of the battery and end at the negative. Since I am integrating over a loop, I'm going to say that's equal to E dot dl. Same thing, same thing. And so the first thing I come to is my resistor. If I start here and I make all my DLs, there's my DL, and I go clockwise here, first thing I come to is my resistor. E dot dl is the voltage across the resistor, which we know according to Ohm's law is just I times R, right? The voltage across the resistor is going to be the current, which is the same current through every element here in the circuit, going to be V times I. I mean, V is I times R. So I don't need to evaluate any integral here. I know that the voltage difference across this is going to be I times R. dl points this way. Electric field points that way, right? So the integral, so IR is actually going to be positive, right? But notice I have the negative here in front from our general equation for potential difference. So I'm just going to put IR, that's the first thing I came to, the resistor, positive to negative. If I integrate in that direction, E dot dr is going to be positive, E dot dl. Then I get to the capacitor. Well, when I integrate E dot dl, again, it's just the voltage across the capacitor. The voltage across the capacitor is charge over capacitance. That's on the formula sheet. It is positive because electric field is in the same direction as dl. But again, I have the negative out here in front. The negative isn't going to be important. That's what I'm getting at. Okay. And then I get to the battery. Well, the battery dl is in the opposite direction of E. And so I will actually have the negative voltage, right? And again, that's the integrating E dot dl just gives me the voltage of the battery as I do that integral over the battery. And so all that equals 0, right? Why am I doing this? Because now I just divide both sides by negative 1, right? Or I just distribute the negative 1 over, and I get the same thing that most students in introductory physics learn. You get a voltage gain from the battery you get a voltage drop across the resistor, you get a voltage drop across the capacitor, and the sum of all voltages is 0. Right? What's that?
Who would have thought?
Who would have thought? So this is the same, literally the same thing. We can see that, yes. If I distribute the negative over, I have negative IR minus VC, Q over C, plus V equals 0. Same thing. Okay? Does that make sense? All right. Because when I have an inductor in here, you can kind of use that the basic, you have voltage gain, voltage drop. Voltage gain, voltage gain for battery, voltage drop for everything else. But in an inductor, you actually don't have a voltage difference across the inductor because you have the same current running through it. And we assume that its resistance is 0. So it doesn't have a potential difference across an inductor. So to get the equation for an inductor circuit, first of all, because it doesn't matter when we have a closed loop, only if we have a closed loop. If we have a closed loop, then the negative doesn't matter because it's all going to equal 0, right? We know the voltages around any closed loop are going to equal 0. So the negative doesn't matter, so I'm going to drop it. And so I'm going to say the potential difference, the sum of all potential differences, is going to be the integral over the closed loop of E dot dl as I go around the entire loop. Okay? But if, I'm going to take out the capacitor because I don't want to have capacitors and inductors in the same circuit yet. But if I put an inductor in here, again, you can't put a plus here and a negative there because the charges lose no energy. The charges lose no energy as they go through the inductor. They're not doing anything. They're not accumulating on the plates of a capacitor. They're not generating heat like they do. Yes, they're generating heat, but that's because of the resistance of the wire. But with a superconducting inductor, no energy. No energy is being used as you go through the inductor. But what is happening is that you're generating a magnetic field as the current changes. As the current changes, you generate a magnetic field within the inductor, and that magnetic field, if that magnetic field changes, then you get a magnetic flux. If you get a magnetic flux, you get an induced voltage, and then that induced voltage creates an induced current. That is what affects the circuit. Okay, it's not like you have a resistance here, but it acts like a resistance. So it will create an induced current that will oppose the actual current that's being driven by the battery.
That's how I was asking.
Yeah.
What if you're an alternating current in there where it's always changing?
Then, yeah.
Then what?
Well, what?
Then is it constantly, then will it heat up? You do that?
The heat comes from resistance. The heat comes from resistance. If you constantly change the direction of the electric current, then you're constantly changing the magnetic flux. And so you're kind of jumping the gun here. We do want to talk about, well, Dan Fullerton will talk about it in his inductor capacitor video. But yeah, inductors in series do certain things. Inductors in series. Inductors with direct current do certain things. Inductors with alternating current do other things. But it's not going to generate heat. What it's going to do is store energy in the magnetic field, and then that as stored energy can then drive current. The video that I'll show you in a few minutes will hopefully kind of get what I'm trying to get my brain into words, but can't really do it. Yeah.
Would the resistance created by the inductor also be measured in ohms?
No, it's not resistance. It's not resistance. It's technically an induced current due to the induced voltage.
Fake
Okay.
resistance.
What's that?
It's
Fake resistance, yeah. The point that I'm getting at is that to go from here to here, right? Well, that's essentially what I'm getting at. But now, technically, and this is a technicality, if I evaluate that integral over the closed loop, this closed circuit loop of E dot dl, if there's no inductor here, that equals 0. Because Kirchhoff's voltage law says the sum of all voltages around any closed circuit loop is 0.
Yeah.
If I have an inductor in there, it's not going to be 0. Because we showed already with Faraday's law that the integral of E dot dl when we're dealing with an inductor, when we're dealing with electromagnetic induction, is equal to the negative d phi b dt. Right? You don't have to remember what I'm about to tell you, but if you want to truly understand it, then you want to pay attention. Okay? Because when I do this now, when I integrate E dot dl, and let's again go clockwise. Well, let's actually start from the resistor. We'll start from the resistor and go around and end up with the inductor. Well, when I do the integral here, I get a positive I times R, right? E and dl are in the same direction, so I get a positive I times R. Then I come up here, I get a negative V, right? Again, I'm just integrating E dot dr, E dot dl, which just tells me a voltage. So I have minus voltage, and that's going to equal, because we don't stop there, we then do the integral of E dot dl as we go across the inductor. But because the charge here is the same as it is there, the voltage is the same because there's no voltage drop, because we're going through wire, which we're assuming to have zero resistance, even if it's coiled up, doesn't matter. The electric field in here is zero. The electric field in the inductor is zero. The magnetic field, if the current's changing, is not going to be zero, but the electric field's zero just because you got the same potential on both sides of the inductor. There's no loss of electric potential. Okay. And so when I do E dot dl for the inductor, it's zero. There's no voltage across the inductor. And so all that together equals negative d phi dt. D phi photon. Yes. And I also know that phi b is L times I, and d phi b dt is L di dt. And so I can rewrite this as IR minus V equals negative L d phi dt. And notice I can move everything to one side, in which case I can rewrite this as V.
Should be negative dl di, not permanent I.
That's what I said. That's what it says. Gosh, I need glasses.
I have glasses.
I don't know how to follow that up. But notice I can rewrite this as V minus IR minus L di dt equals 0. So some students, some teachers will tell you that just assume there's a potential difference across L and call it L di dt.
But not you,
Right.
Mr. Graham.
Well, because not Walter Lewin, who I based my notes off of. Right? It's not because I'm a genius or anything. So you could just say voltage here, voltage drop here, where voltage drop is kind of like L times I, but not really. So yeah. But if you wanted to kind of think of it that way, then you're okay. You got a voltage gain from the battery, you got a voltage drop from the resistance, and then you got that weird L di dt around when it comes to the inductor. Okay. So this is taking more time than I thought it was going to. I know this is fast, but
Does that end up becoming a differential equation?
does it become one?
Because you have it.
I and di dt, so it's a differential.
It is one.
Okay.
Yeah.
All right.
We got I, because what's changing here? When I close this switch, what's changing?
Current.
The current's changing, right, as a function of time.
Yeah.
It will reach a steady state at some point, kind of like when you charge a capacitor. So what do you think ends up being involved in the equation here? The solution to this equation?
Natural log E.
Natural log. Yeah. You want to do it real quick?
Yeah.
Okay.
Someone's gonna stop.
So I'm going to divide up both sides by R. You have R minus I. I mean, this might take a minute. Do you guys have questions about the assignment?
Yeah.
Because Mr. Fullerton does this.
Okay. Yeah. Well, if he does it, we don't need to see it from the
What you end up with is the current equals the maximum current, which is the current that it will attain after a long time, times 1 minus e to the negative v over r times t. V over r. R over... No. What am I talking about, v? R over L.
Yeah, gospel Suzanne.
Sorry.
I can't believe you.
So it's very similar to the capacitor charging and discharging equation, but instead of 1 over RC, T over RC, it's T times R over L. Right. All right. I'm going to extend the due date to the... I'm not going to make the current quest due tonight. Tomorrow night.
I have so much to do tonight.
Okay. Then I'll make it due tomorrow night then. Because I do want to show this video. I want to make sure you guys see it. So yeah. Remind me at the end of the period to do that.
Do it.
At the end of the period.
It's in the
Oh my god.
Are we still gonna look at
We still have a
Yeah.
class left.
Okay, I'm gonna extend the due date till tomorrow, and then because we're not gonna have that much time today. This took longer than I thought it was going to. Remember all this stuff because we're gonna have one more quest assignment. I'll make it relatively short, but it is gonna cover all the. It's gonna have just like one question for each main
I
topic
was
here.
planning on forgetting it before the AP exam.
Yeah, I figured. That's why I'm telling you not to.
It was my direct intention
Are
to
we gonna
forget
have
all
a-
of the knowledge I've gained.
a quest?